the first thing that we are going to, data link layer has 5 responsibilities, if you remember. Error detection and correction, or error detection, error control, flow control, medium access control. You remember framing? There were 5 physical addressing, 5 responsibilities. So we now have 5 chapters in data link layer. We have to discuss about each responsibility in detail, right? But they are interesting topics. Stick with me, they are interesting topics. Okay. So the first responsibility, or the first chapter that we are going to start with in data link layer, is error detection and correction. So one of the responsibilities of data link layer is, while sending data frame from one node to the other node, when a data frame is being sent from a node to a node, if an error happens in between, how the receiving device's data link layer will understand it, will detect it, or if it can correct it as well, right? So all these techniques are already completed in our lab. Let us quickly brush up. Wherever there is a scope for going in deep or depth, I'll stop at that particular technique, okay? But rest is all understood by you in the lab itself. So the thing we are going to discuss is error detection or error correction. Obviously, we have to first understand what an error is. Now, what is an error? Once a data is being transmitted from one device to the other device, if one of the bits gets changed from 0 to 1 or 1 to 0, we simply call it as an error, as error has been occurred during the transmission. There are 2 types of errors, single bit error and a burst error. This is all finished. That's why I'm quickly going through the slides, running through the slides. So what is a single bit error? Out of the data transmitted from sender to receiver, only one of the bits gets corrupted. Either a 0 becomes a 1 or a 1 becomes a 0. Then we call it as a single bit error. Example is given there for you. But in communication, generally single bit errors don't happen. The other type of error called burst error is the most common error that can be encountered, or that can happen during a communication or during a transmission, right? What is a burst error? If more than 1 bits are corrupted during the transmission, they need not even be sequential. They need not even be side by side. There can be any number of bits that are corrupted over the transmission, not even consecutive bits. Then we call it as a burst error. Example is given there for you. There are 3 bits corrupted. 2 of them are consecutive. 1 bit is a bit far away from them, a little bit far away from them. But still, we call that entire range as the burst of the error that has occurred. That is called as the length of the burst error that has occurred. So more than 1 bit gets corrupted, we call that as a burst error. Can you mute? Ma'am, Sumata ma'am, can you please mute? Right. So our technique is our concept is error detection. So to detect or correct errors, we need to send redundant bits along with data. I've told you, every error detection and correction technique, whatever technique it is, all of them have used additional bits. And those bits are called redundant bits, right? 153, that's good. I can log the session in 1 or 2 minutes. Okay. To detect or correct errors, we need to send redundant bits along with the actual data. That's our goal. So how it actually works. Look at this slide. You should easily understand what we have done in all the error detection and correction techniques. On the sender side, a message, a blue rectangle, you call the original message. The original message is put to something called a generator. What is the role of a generator? Generator generates additional bits that are supposed to be appended to the original data. Redundant bits are generated by the generator. Now, once we have a generated something, then I have a yellow rectangle, the original message, along with the generated bits called redundancy bits. All of them put together are transmitted onto the right side now. Now, while being transmitted, why we actually have this topic? Because we are communicating through an unreliable transmission. We are not sure whether it's exactly received by the receiver or something goes wrong in between. On the receiving side, now the received information, the yellow rectangle, received information is put to something called a checker. What is the role of a checker? It checks whether there is an error according to the role given to it, according to the logic given to it, according to the program it has, right? Then if an error is detected, it is discarded. If not, original message is received by the receiver. That's the blue rectangle. In between that, you can see correct or discard. If it is correct, it is received. If it is wrong, it is discarded. This is the simple procedure of error detection and correction by adding additional bits to the data. Now, what we have to commonly understand is, in error detection and correction technique, we use a technique, or we use concept called modulo n arithmetic. In CRC, do you remember that I told we use a division called modulo 2 division or modulo 2 addition or modulo 2 arithmetic, if you remember that from the lab session, right? So I will not simply say modulo 2 here. Instead, I'll put a heading called modulo n, right? So modulo n arithmetic is generally used to generate the redundant bits in most of the error detection techniques. Even parity check also uses modulo n arithmetic. I did not tell you in the lab session because that becomes a complicated thing, or in the beginning itself you may get confused. So I just simply said parity means count the number of ones, but it's not true. It's not the way it happens. Generally, the technique is it uses modulo n arithmetic operations to generate redundant bits, and most of the error detection techniques use modulo n arithmetic. Then in modulo n arithmetic, we use only the integers in the range 0 to n minus 1. Inclusive means 0 is also included, n minus 1 is also included. So what does this mean? In CRC, what did we use? Modulo 2. Substitute 2 in place of n. Substitute 2 in place of n. So the range of integers that we will use will be 0 to n minus 1, which means 0 to 2 minus 1 is 1. Did we ever use any other bit other than 0 and 1? Did we at least have a carry generated, third bit generated? Nothing. There was no carry generated at all. Why? Why? Because we use modulo 2. Modulo 2 only uses 2 integers, not more than 2 integers, 0 and 1. Okay, right. So here we will not stick to 2. Instead, we'll say n. Modulo n uses the integers from the range 0 to n minus 1. Right. Then how does it work? Here is an example of modulo 2, which is already discussed by me in the CRC lab session. In a modulo 2 arithmetic operation, I told you that addition and subtraction will give you the same result, if you remember, right? I have A, B, C, 3 rectangles there. Look at A. 0 added or subtracted with 0 will give you 0. 1 added or subtracted with 1 will give you 0. I told you addition and subtraction modulo 2 will give you the same result, right? Then the second rectangle, 0 added or subtracted with 1 will give you 1. 1 added or subtracted with 0 will give you 1. The plus with circle is an exclusive OR symbol over there. Simple exclusive OR operation. Modulo 2 simply uses or is a simple example of exclusive OR operation. Now my C, the third rectangle on the right side, is an example of 2 bytes or 2 words added. Look at that. 0 and 0 gives you 0. 1 plus 0 gives you 1. 1 plus 1 gave you 0. No carry is generated to the next position. No carry is generated. Then 0 plus 1 is 1. 1 plus 0. 1 plus 1 is again 0. No carry is generated. So that's how a modulo 2 arithmetic or addition operation works. Is that clear? Now, so keep them in mind and let us now quickly go through all the concepts of error detection and correction. An error detecting code can detect only the types of errors for which it is designed. Always remember this. Every error detection code will always detect an error is false. If somebody asks you a general question in your interviews or somewhere, does an error correcting or error detecting code identify all the errors? No. It can only identify the errors that it is designed for, not all the errors. Always remember. Other type of errors may remain undetected. That is what you are always supposed to remember. Now, these are the techniques which we have already finished. Error detecting techniques include 4 of them: simple parity check, 2-dimensional parity check, checksum, and CRC. Error correcting technique, there is only one technique in our syllabus. We use Hamming code. Done? Let's quickly run. Simple parity check. In my explanation in the lab, what did I tell you? Take a data word, count the number of ones in it. Now I'll go the other way now. You can change your program according to my explanation now. If you want, you can change your program. Already written program is just counting number of ones. Now it is not the case. I am going to show you the actual hardware logic, how a simple parity check works. It is not a program that is counting zeros and ones. It's a different program. It's a different thing, right? So how a simple parity check works here. This is generally what I have explained. Number of the data on the left side, center side, 1000111 is put to a parity check. Simply count the number of ones. I have 3 ones there. 3 is odd. And in my example, even from the beginning, even till the end of computer networks class, we'll be taking always even parity. Remember, we'll always take even parity. So since I want to take even parity, number of ones are 3, which is odd. I wanted to make it even. So additional 1 is added to it before sending, before transmission. Then on the receiving side, again, the number of ones are counted, whether you want to accept the data or discard the data. That's it. That was very simple. But the actual logic is like this. Those who are closely trying to understand how the hardware or how the actual implementation happens at the data link layer, if it is simple parity check. Look at this. Let us assume that there is a data, 4 bits of data, and I'm just saying that it is A0, A1, A2, A3, or simply you can just take 1, 0, 1, 1, whatever the data it is. How a simple parity check works. Look at this, very simple technique. Let us assume that there are 4 bits in a data to be transmitted, 1, 0, 1, 1. Is this visible?
Yes, sir. Visible.
Yes, okay. Only Manoj response most of the time. Good. Right. So now those 4 bits are put to a generator. Look at that. All the 4 bits, when they are coming from the top, before they are transmitted, in between they are now put to something called generator. I have shown you the logic. The second slide before I started. Actual data put to a generator. Generator generates redundant bits. They are added with the actual data and then sent to the receiver. Right. So now I am putting, now the data is being forwarded or placed through a generator. Now, how does this generator work? Here, it is not counting number of ones here. Instead, what it does is it adds modulo to addition or modulo to arithmetic. Take the first bit of the array. Now you have to change the program like this. Take the first bit of the array, read the first bit of the array, add it modulo to addition with the second bit of the array. 1 plus 1, what will you get? 0.
0.
Right? Now this result is added to the next bit in the array, next location's data of the array. 0 plus 0,
0.
again you get 0. The next result again is added to the next bit in the array. 0 plus 1 is 1. That is the answer you get. If you count the number of ones, 1, 2, 3, 3 is odd number. What should I place? 1. What is the answer I have got here? 1. That's how the logic works. It's not just counting number of ones, because the program should be easy. I've told you the general way a lot of people talk, but that is not the actual hardware implementation. This is the implementation part of it, right? So now once I put to generator, generator has generated me 1 redundant bit, additional redundant bit, which is 1. That will be now added to my actual data, right? So actual data plus redundant bit is added, and all that is transmitted to the receiving side. Fine. Now receiver receives all this data on there. Now see, before it is put to a design logic, again it is put to something called checker. Now what is the logic of checker? What does a checker do? A checker generates a syndrome. What is a syndrome? Syndrome helps the design logic to understand whether there is an error in the data or not. That is the logic of the receiver. Receiver puts the receiver data to a checker. Since generating on the sending side, it is generator. Here it is checker. So it is put to a checker. Checker will do something on it and it will generate a syndrome. That syndrome is useful for the design logic. See, checker, above the checker, it goes to something called syndrome. From the syndrome, it goes to something called logic, design logic or decision logic. That syndrome is taken by the decision logic. Decision logic will now either say discard the data on the right side or to the top, accept the data. If it is fine, accept the data. If something is wrong, discard the data. So what does the checker do here? It should generate a syndrome now. How is the syndrome generated? The same thing again. 1 is added with this 1. What is the answer? 0. Modulo to addition always. Yes. 0. 0 is added to the next bit. 0 plus 1 is 1. 1 is added to the next bit. 1 plus 0 is 1. 1 is added to the next bit. 1 plus 1 is 0. That's it. That is the syndrome generated. That 0 is given to decision logic. Simple if-else loop in decision logic. If syndrome is equal to 0, accept data. If syndrome is equal to 1, reject data. Let us assume if one of the bits is corrupted. What will be the answer we get? It will be 1.
1.
Yes, it will be 1. You can check it if you want. You can add and check it. If one of the bits is corrupted, the answer will be 1. Syndrome will have a value 1. that is given to decision logic, data is discarded. Is that clear? So that's how a simple parity check works, not counting ones. Generally, whenever someone asks you in the exam, you can just say counting number of ones. But if someone really asks you the implementation of simple parity, this is what you should say. The bits are put to a generator. What has happened in a generator? Here, that is my slide. R is the redundant bit that is generated on the generator side. A3 plus A2 plus A1 plus A0. I have added 4 bits on the sending side. That will be R0. Now on the receiving side, a syndrome is generated, S0. S0 equal to received bits, B3, B2, B1. Why did I put B3, B2 instead of A3, A2? I don't know which bit gets corrupted. I can't just say again A3, A2, A1. That is wrong. I have to treat them as separate things. Sending data is separate, receiving data is separate, unless I confer that they are exactly received as the sender. So I'll say B3, B2, B1, B0 plus that R0, which is generating a Q0. Right? And then finally, what is the conclusion? If F0, the syndrome is 0, there is no error. That's how a simple parity check works. Done. Now I have 5 cases here. Let us look at a simple example. Assume the sender sends a data word 1011. Oh, exactly the same as I have received. I have written here 1011. The code word created from the data word is 10111. Now, someone has to tell me the difference between data word and code word. The actual data word is 1011. The code word is 10111. So a data word means, always remember in my next slides from now on, I have about 50 slides now in this chapter. So from now on, whenever I use a word called as something called a data word, which is actual data, which is not added with anything. Is that clear? Then what is a code word? Code word means data word added with redundant bits. Whatever technique it is, it could be CRC, it could be Hamming code, whatever it is. Data word means unpadded, unadded actual data word. Code word means data word along with additional bits or redundant bits added to it. So this is my data word, this is my code word according to my example. Now there can be 5 cases. The first one is the receiver receives, no error occurs. The received code word is as it is, 10111. The syndrome is 0. The data word is created. What is the data word? 1011 is created. Fine. Second, one single bit error changes A1. Let us assume this is A1. One of the bits got corrupted. What will happen? Syndrome becomes 1. Data word is not created. Instead, it is discarded. That is very simple. Third one, one single bit error changes this bit. That is redundant bit. That is not actual data. Still, what will happen? What will happen? Syndrome becomes 1 again.
1.
Again, data word is discarded. That is the third scenario. Fourth scenario, an error changes 2 bits. Any 2 bits. Here I have written one of this and one of this. Any 2 bits are changed. Now let us see this. Let us see how a syndrome is affected by changing 2 bits. You already know that, but still, let us just calculate and show. Let us assume that this is changed to 0. And this is also changed to 0. 2 bits are corrupted. Let us now calculate the syndrome. 0 plus 1 is 1. 1 plus 0 is 0. 0 plus 0 is 0. 0 plus 1 is 1. See there?
1 sir.
Sorry, did I do something wrong?
Sir, 1 plus 0, 1 item is 0 on here.
0, right? Where is it? Here. Yeah, that's what I'm checking. Syndrome should be 0. Right. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 1 is 0. See? Still, there were 2 bits affected. The syndrome calculated or checked is 0, where the data word is wrongly received, is wrongly created. So what will be the data word created on the receiver side? 1001. But what was the actual data word sent? 1011. That's the mistake. That's the problem with simple parity check. If 3 bits are corrupted, the last category or criteria there, if 3 bits are corrupted, again, syndrome becomes 1, data word is not accepted. So what would be the conclusion? A simple parity check can detect an odd number of errors only. Even number of errors, if they are occurred, the syndrome becomes 0. Data word is wrongly created. That's the problem with simple parity check. So to overcome this, we went to the next technique called 2-dimensional parity check, where the data is broken into pieces, or they are arranged like that. For every row, there is a row parity calculated, just like your simple parity check. But additional to that, even for the columns, a additional parity bit is also calculated. Hope you all remember this, right? Very simple technique, right? So
Yes,
this is
sir.
my example here. Some rows, 4 rows, all red colored bits are my parity bits. Okay, so first row has 1, 2, 3, 4, 5 ones. So my parity bit is 1, and so on, which is already completed. I don't want to waste time on this. So here I have few examples, not two. I have few more examples to tell how a two-dimensional parity works. Let us assume one of the bits is corrupted on the left side. Something in the rectangle or a square that's supposed to be 0, it became 1. Okay, it became 1. Now what has happened is, in the earlier case, row parity and column parity, not the row parity on column parity. Both of them, any one of them should get affected. So simply speaking, one error affects two parities. Then the second diagram there, 2 bits are corrupted in the same row. 2 bits are corrupted in the same row. Row parity does not get affected. Should I show you again? Row parity does not get affected, but 2 column parity bits got affected. That is what I wanted to prove you. Even if it is even number of errors that happen in the same row, in simple parity check, it wasn't detected, but in two-dimensional parity check, it can be detected. Then my third example, 3 bits are corrupted in 3 different rows. Still, can they be detected? Yes. Fourth example, finally, in my gray shaded rectangle, there is one pattern of corruption of data where it cannot be detected. If even number of bits are affected in even number of rows, and the bit position of the affected bits is exactly same, then an error cannot be detected in two-dimensional parity check. That was the disadvantage. We even have written a program for this, right? So let us just quickly move from this. Then we went to checksum, if you remember. So checksum is very simple. I have taken an example there. Let us assume that there is some data to be transmitted. 7, 11, 12, 0, 6. In brackets, I have written there. 7, 11, 12, 0, 6. So what happens in checksum, or what happens in this, a simple technique is to detect an error, add all these 7 plus 11 plus 12 plus 0 plus 6. What is this? Some 36. I have written there in red. So along with this, send 36. Along with this, send 36. And the receiver will receive all this along with this 36 also. It will add these and see whether the addition is equal to 36 or not, then accept it. This technique is called sum, not checksum. This is called sum. Checksum is like this. My second example. If send all this as it is, of course, the same thing, add all this, it becomes 36. Instead of sending 36 along with them, send minus 36 along with them. So what happens on the receiver side? It adds all of them. Instead of checking this with this, all that is gone now. Simply add all of them. 36 plus 36 minus 36 gives you 0. If the result is 0, accept the data. If not, reject the data. This is a simple technique. This is checksum technique. Right? This is already implemented in your lab again. So checksum. On the sending side, message is divided into 16-bit words generally. Generally, that is the case in checksum. 16-bit words. The value of the checksum first is set to 0. Initially, there will be checksum which is 0. Now, what should happen? All the words, including the checksum, are added. All of them are added. So initially, this is 0. Remember. Initially, this is 0. Remember. So what is happening? 7, 11, 12, 0, 6, and 0 is also added. Let us just assume that this is something 4 or 2. Plus 0 is my checksum initially. All of them are added. Then you will get a value. Right? Then once you get the value, that value is called sum. Now what should you do? You should once complement that sum, or invert the sum, or complement it. It becomes a negative value. Now that value is called checksum. Now this 0 is replaced with that checksum and sent along with the original data. That is the sending side of checksum. Then on the receiving side, again, along with checksum, everything is added. Sending side is performing addition, the receiving side is also performing addition, right? So everything is added. Now, once you get a value, that value is complemented. If the complemented value is all zeros, then it is actual data without any corruption. If the value generated after adding all of them is non-zero, simply we say that an error has occurred during the transmission and the data is rejected. Is that clear?
Yes, sir.
Any doubts till now? Yes, good. So this is all already learned by us. Now, what I'm going to do is next two techniques or next technique, especially CRC, I'm going to go very deeply into it. I'm not going to just teach you as if I have done in the lab. I want you to understand it thoroughly. One of the interesting, important techniques, right? So let us just quickly look at some example here. This is the same example I've taken you in the lab session. Same example. Adding all of them, implementing checksum, and then adding along with checksum should give you all zeros, right? Just go ahead. We'll just go ahead because that is already completed. Now we go to this most interesting technique. Now what I want to do is just like simple parity check. I want to show you the actual implementation of CRC. Done, right? So unlike your parity check, two-dimensional parity check or checksum, they are all based on addition. They were all based on addition, isn't it? Even simple parity check is not counting. I've told you it is addition, modulo 2 arithmetic, right? So all those techniques are based on addition, but CRC is based on division. Right? So unlike checksum scheme or any other scheme which is based on addition, CRC is based on binary division. We already know this. So how CRC works, I don't want to talk about the entire slide. How CRC works, this is already explained. Take the original data, then we will have a predetermined divisor. Then
n-1 redundancy.
Bits, yes. How many bits are there in the divisor? Let us assume it is n. Then we append n-1 zeros. In my example, it is n zeros there because I have just thought of the divisor is n plus 1. However you want to take it, n n-1, n plus 1, n 1 less than the number of bits in divisor. Those many zeros are added to the actual data. Then all that is put to something called a divisor. That I have seen in my example, it says n plus 1 bits. Okay, right. So let us assume n plus 1 here. Then we get some CRC remainder, which is n bits again. Now those remainder bits are replaced in the place of actual appended zeros. So data plus CRC bits are sent to the receiving side. Now data and CRC bits are divided by the same divisor as the sender. If the remainder is 0, simply accept the data. If not, reject the data. Now I'll tell you why division will not generate a 0 remainder if something goes wrong. I'll go a little bit deeply into it. So please try to stick to me. Some slides are a bit tricky or a bit, complicated. Not really complicated, a little bit complicated. So try to stick to me and follow what I'm saying so that you understand it. So this is the actual concept we understood, right? So I'm just showing that in the form of the diagram that I've used for simple parity. Same thing again. Let us just assume there are 4 bits, A1, A0, A0, A1, A2, A3. They are put to something called generator. Now look at generator. Generator has 7 inputs instead of 4. Generator has 7 inputs. 4 are the actual data. 3 are the appended zeros. Why 3 zeros are appended? If you look at something in between both the rectangles, there is a gray rectangle, small gray rectangle. D0, D1, D2, D3, which is a divisor. How many bits do I have in the divisor? 4 bits. So how many zeros? 3 zeros are appended. Good, thank you. Then once the generator is put with those 7 bits, it generates only 3 remainder bits. 3 bits are coming out of it. See there? Then actual data bits plus the generated 3 redundant bits are sent to the receiver. Receiver will now take those received 7 bits and they are now put to a checker. 7 input bits are put to checker. Checker uses the same divisor. Look at that gray is again given to the checker side. It uses the same divisor to divide. It generates a syndrome. See how many syndrome bits are generated? n-1 again. n-1 syndrome bits are generated. If divisor is n bits, n-1 syndrome bits are generated. Now that syndrome bits are put to a decision logic. Very simple. If all of them are 0, accept the data. If all the syndrome bits are not 0, reject the data. That's it. Half an error has been occurred. This is my logic, right? Let's see now. This is an example, right? So according to this example, what is my data word? 1 0 0 1. I have written it on the top. 1 0 0 1 is my data word. What is my code word? At the bottom, 1 0 0 1 1 1 0. It is added with CRC bits. All that put together is called code word. Remember, so actual data is data word. Data word along with generated redundant bits put together is called code word. The left one, 1011 in the example is divisor, right? Let us, should I have to explain all this again? Should I show you again how is it working?
No, sir.
Anyone?
No, sir.
No? Sure. Anyone wants to know how is it working? It's already done, right? You have already written the program. I think 130 people have submitted their assignment, so that should be done, right? So that will now put to a division logic, and then 110 is generated as a remainder. Now that will be added to the actual data. So my data becomes now 7 bits. 1001 110 is my data. Now that is sent to the receiving side. I have two examples there. One example is data not corrupted, 1001 110. Second example is one of the bits is corrupted. That red bit 0, I have made it 0. So you can clearly see in both of my examples, when data is not corrupted, the receiver, when divided by the same divisor, yielded a syndrome 3 zeros. Whereas on the second example, the receiver upon dividing the same receiver data with the same divisor yielded a syndrome which is non-zero. 011 is the syndrome that has been generated there. So in my first example, data word is accepted. In my second example, data word is rejected. That's how CRC works. Is this knowledge okay? Can I now go deeply into it? Can we start going a little bit deeply into it now? So this is the implementation logic. It looks clumsy, isn't it? But this is the program that you are supposed to write, not the actual general program that we have written. This is how the implementation part of it looks. From the top now, right? So look at the augmented data word on the right side, augmented data word, which is not the code word. What is the difference between augmented data word and code word? Augmented data word means actual data plus zeros added to it. Code word means actual data plus redundant bits added to it after division. Yes, that's what you should understand now. So 1001 is my actual data. Then 3 redundant or additional bits, n-1 additional bits are added to it. I have 1001 000 put to a, if you're CSA or COA, what is the subject you have read in second year?
COA.
COA. If your COA concepts are really good, you should easily understand this. Did you come across some concepts called shifters, counters?
Yes, sir.
And even in MPES, you should come across rotate, swap, exchange, and shift.
Sir.
Yes. If your concepts are good, this is a simple technique, right? So now that is put to something. See there, I told you that it is put to what? A plus symbol, exclusive OR. What is exclusive OR used for us here? We are using modulo to arithmetic. We are using modulo to arithmetic. So now here is my word 1 0 0 1 000. Is it the first one on the top now? Now, initially, what is the value that we are using? 000, all zeros, right? So look at the array there. Look at the array to that on this side. Look at the array. There are 3 positions. Why 3? n-1. Remember, we are trying to calculate redundant bits. How many redundant bits will we get? n-1 redundant bits should, yes. So that's what we have, n-1 locations in that array. I have it like this: 1, 2, 3, right? So initially they are fed with some input from the top. Can you see this? Can you see that? What is the input that is fed to them? All zeros initially, all zeros, right? So it gets 0 here, it gets 0, it gets 0 here. Now this is fed to this, right? So now 1 is added to that exclusive. Sorry, I should have written it here just a little bit. Okay, look at the first step from that side. 1 is added with the first bit, 0 fed to it. 1 plus 0 modulo 2 is 1. Look at that, that goes to the next, which means the array values get shifted. I think, who is that? F1 or someone, G9, was trying to implement this logic. I don't remember exactly, F1 or G9. Someone of you, both of you, were trying to implement this logic of shifting your array elements. Now, this is what exactly happens. Now, when it goes to the next location, see there, 1 on 0 gives 1. Can you see the dotted line going down? That is 1 there. Then again, 0 on 0 to the next location. 0 on 0 to the next location. Now my array elements have changed from 000 to 100. Is that clear? Again, now once I have 100, now I have one more shift in the actual data word. The first one is gone. Look at the second step. I have 00100. Instead of 100100, this is gone now because one iteration is finished. One shift is finished, right? So now I have the next bit coming in, 0. Now, what do I have the input from the top? The last bit is given, is fed as the input. Can you see that yellow rectangle box is fed as an input? Now, again, I have a question. It is fed as an input to only 2 locations, not the third location. Can you see those arrow marks from the top? 2 of them are attaching to that top line, but the last one is not attaching to it. It is always by default 0. Can you see? Can you see that yellow rectangle box just beside it? The top always 0. Why? Can anyone answer me that question? Why it is always 0? Why that most significant position is always given with 0 input? Can you look at this example? Not this, generator. I want generator example here. Every time something is added, look at the black bits generated, not the pink bits. After a pink bit is added, once the first step is 1001 is my actual data. To that, pink is 1011. Look at what is generated, 0100. Is it? What is the leftmost bit? 0. Again, wherever you see, wherever you go, you will get, whenever you multiply with 1 or whenever you take 1, the top, whenever you get there 1, you'll get the leftmost bit as 0. We'll discard it, right? So obviously the most significant position will always be 0. Are you understanding? Or is it becoming complicated unnecessarily? If someone is not understanding the actual logic or implementation here, don't worry, you can stick to that simple logic that we have discussed, simple addition, that example of division that I have shown 2 slides back. You can stick to that. But this is the actual implementation inside, right? So if you thoroughly go through each step, you can see it. It is shifting. From the right side, now you can see step by step the number of bits come into the array, into the shifter. And then they go, keep modulo arithmetic addition keep happening. Whenever there is a 1, you can see, sorry, I wanted to mark it, but I don't know if annotation is on or not. Whenever there is a 1 generated on the yellow rectangle on the left side, whenever there is a 1 generated on the yellow rectangle, what did I multiply with? Can you see here?
0.
Yes, I multiplied with 1. See here, yes. So whenever there is a 1 generated, look at what is being fed to the positions. 1 is being fed. Look at it. From 1, there is an arrow going out, red arrow, pink arrow going out. It is being fed to 2 locations. But the third location is always 0, remember. The most significant position will always be 0. When a 0 is generated, 0 is fed to the logic. When a 1 is generated, 1 is fed to the logic. It's just like 0 means multiplying with 0, 1 means multiplying with 1. That's what we did in the example. Whenever the last position is 1, multiply with 1. Whenever the last position is 0, multiply with 0. That is what I have told you. Yes? So that's what I'm doing here. That's it. Just simply sending it as an input to that side. So finally, when you keep shifting it, you try it on your own. I don't want to explain all those steps here. It's it takes a lot of time and the board is not sufficient. Look at the last 3 bits that are generated. 1, 1, 0. You try it at your home. Just a simple logic of modulo to arithmetic and shifting and rotating. Shift, rotate. That's the simple logic here, right? Done. So look at the last 3 bits, 1, 1, 0. Now go back to this slide. What is the syndrome? Sorry, what is the remainder generated there? 1, 1, 0. So this is not the logic. This division is for understanding purpose. This is the actual logic that is implemented inside in the data link layer if CRC is used. That is the concept. So if you have written a program for the division, which we have shown a couple of slides back, if you can change your program to this, which means you are actually implementing CRC the way it is supposed to be implemented as a program. This is the logic that you're supposed to write. Okay. So what I didn't tell you this in the lab time because writing logic for this is not, it's not that simple. You may, break your head unnecessarily. That was the easy logic. Try to write some program for this if you can, right? So that's the actual implementation. But this is not over yet. CRC is not just a simple technique like, it just came out from nowhere. It has mathematical roots to it. The theorem, it's just like a theorem here. A theorem needs a proof. If you remember your 9th, 8th, 10th maths, whenever we have a theorem, we have a proof. How to prove it, right? Similarly, the CRC here is not just a simple technique. It has proofs on how it actually works, how exactly it detects an error. And why did we use that divisor of something? And then why did we append n-1 zeros? There are a lot of mathematical rules that have gone into it, right? So if you have to understand it, first we have to start understanding from this slide. Polynomial to represent a binary word. This is where everything started. So my data word, you remember, let us assume that according to this slide, I have 1, 4 zeros, 2 ones is my data word. So how is it represented as a polynomial? So start from the leftmost significant bit. My first rectangle, leftmost significant bit. 1 into x power 0 plus the next bit is 1 into x power 1 plus the next bit is 0 into x power 2. I'm changing the locations now, x power 0, x power 1, x power 2, x power 3, and so on. Similarly, the last one is 1 into x power 6. So if I represent all that data word as a polynomial, I'll get x power 6 plus x plus 1. Only those polynomial values are retained where it has 1 in the position. All the 0 positions are gone. Did you understand that?
Yes, sir.
Yes, sir.
It's a simple representation in polynomial. That's it. Very simple representation as an equation. Now, degree of the polynomial. Always the degree of the polynomial is highest power. You remember that? Yeah, highest power. It is always 1 less than the number of bits. Obviously, because the bit position starts from 0. How many bits do I have here? 7 bits. 1, 2, 3, 4, 5, 6, 7, isn't it? 7 bits. But what is the degree of the polynomial?
6.
That's what. It is always 1 less than the number of bits. So degree of polynomial x power 6 plus x plus 1 is always 1 less than the number of bits in the pattern. When the polynomial code is employed, sender and receiver must agree upon a generator polynomial. What is a generator polynomial? Divisor in our plain terms. We divided with something, isn't it? Same divisor is used on both sides, sender side and receiver side. So here we call it as generator polynomial because if you divide with it only, you got a result. It is generating a redundant data. That's why it is called generator polynomial. So it's called g of x. Remember, g of x. Then I have these representations now. Data word is represented with d of x. What is data word? Actual data word without appending anything to it. D of x. Code word c of x. What is a code word?
Actual data plus
along with
n-1
redundant.
zeros.
Yeah. No, not n-1 zeros. Along with CRC. Yeah. CRC bit added to it. Yeah. Right. So that is code word. Then generator is g of x. What is generator? The divisor. Don't think that I'm talking maths here. It's just I'm giving a hint of maths here. Don't have to worry about it. If someone is scared of maths, there is nothing in it.
Sir,
Generator is, yes.
why will take polynomials in CRC?
I'll show you. I'm going to prove it. I'm going to prove it in my couple of slides, coming couple of slides. I'm going to prove it. That's why I'll tell you that this is not a simple, technique. It has mathematical roots with proofs in it. Okay, right. That's why I'm giving you this introduction slide of mathematics here. Next slide, please wait. Right, generator is g of x. Then what is generated? Syndrome s of x. If something goes wrong, we call it as an error e of x. So I have these few things now. Data word is g of x. Code word is t of x. Generator is g of x. Syndrome is s of x. Error is E of x. Now here is my received word. I'm talking about, because error has to be detected on the receiving side, not on the sending side. So here is my received word. Something has been received. What is received? The code word should be received. C of x. C of x is sent by the sender, isn't it? Sender sends what? Actual data plus CRC bits generated. All put together is called code word. What is code word? C of x. C of x is sent by the sender. So receiver should receive C of x. Let us assume an error has occurred. So what will happen to my C of x? It is added with an error E of x. Some error, one bit has changed, whatever has changed. C of x plus E of x. Now this is what is my received code word. Actual sent code word is only C of x. Received code word is C of x plus error E of x. Now the syndrome S of x, my last line in this slide, is equal to received code word. This received code word should be divided with whom? The same generator again, G of x, right? So G of x plus E of x divided by G of x. C of x plus E of x by G of x. Simply split it now. C of x by G of x plus E of x by G of x. Is that correct? I'm just splitting it, that's it. Denominator to each numerator equation. Now, since C of x is the code word generated, C of x by G of x will give you 0 plus error by G of x will give you some non-zero value. Isn't it? Because this generator is not designed for it. I'll show you why and how. I'll show you. So now, why if the error has occurred? See this now, I'll show you. Here on the right side, second rectangle. What is the answer I have got? 011. Why? Why? Because the code word on the top, see this? See the code word on the top? Is it actually the code word that is sent? No, it is error, code word with error. One of the bit got changed to 0. That is my example, C of x plus C of x there. Is that clear? That will definitely lead to a non-zero result, a non-zero syndrome. You can see it there. If there is no error on the receiving side, C of x by G of x will definitely give you 0 reminder. Obviously, that is how you have defined C of x. Are you understanding? Are you following?
Yes, sir.
Yeah. Okay. Let's see. Good. So this is what is my mathematical implication on CRC. Let us still see. It's not done yet. Here is how my division has happened. So to prove CRC works properly, this is the mathematical example I'm going to take. You don't have to write all this in the examination, but it is my responsibility that my students should understand it from the basics, everything in it. Not just a simple division with numbers. That is very simple. Everyone can understand it. So I'm taking the same example now. I'm going back. So my actual data word is 1. Where should I write it? 1 0 0 1. And how many zeros have been appended to it? N minus 1, which is 3 zeros are appended to it. Right. 0 0 0. This is my augmented data word. Now I want to convert this into polynomials. X power 0, x power 1, x power 2, x power 3. Is it?
Yes,
Plus
sir.
Yes,
x
sir.
power 4, x power 5, ledu, x power 6. So my data word, augmented data word is x power 6 plus x power 3. Now I have a generator polynomial, which is 1 0 1 1. 1 0 1 1. Now I want to convert this into polynomial. X, sorry,
Yes.
not x, my mistake. X power 0 is 1, right? X power 0 is 1.
This one was sir.
Oh yeah, 1 into x power 0, 1. 1 into x power 1, x plus x square,
0.
x cube. X cube plus x plus 1. X square is missing. So this is my generator polynomial. This is my augmented data word. Is that correct? So I have to divide this augmented data word with my generator polynomial. What is the CRC remainder I have got? 1
X
1
square plus
0.
X.
1 1 0, which is x square plus x. That is what I should get. Even if I perform mathematically a division here on the polynomials, I should get x square plus x. Now look at this. Now I'm trying to divide x power 6 plus x cube. Some space is the bound. I'll just remove this. I have to divide this x power 6 plus x cube with generator polynomial x cube plus x plus 1. Sorry, ఇక్కడ రెండే ఉన్నాయి, ఇక్కడ మూడు ఉన్నాయి. Is it okay? Can we divide like that?
Yes.
Look at the degree of the polynomial, please. Yeah, not the terms in it. Look at the degree of the polynomial. This is just a degree 3 polynomial. This is a degree 6 polynomial. You can divide it, right? So now when I divide it, let us just separate, because x power 5, x power 4 can come in between. Let us just separate this x power 6 and x power 3 a little bit. Let us put it a little bit far away from each other. Okay. So x power 6 plus x power 5, x power 4, let us just say x power 3. This is my augmented data volt. So x cube, I should make it x power 6. I should multiply it with
X cube.
X cube.
x cube. That's it. X cube into x cube. X 3 plus 3 is 6, obviously, right? So x cube. This is generator is multiplied with x cube. Generator is multiplied with x into x cube. X power 6 plus into x cube. X power 4 plus 1 into x cube.
X cube.
X cube.
Now, if you remember modulo 2, I told you, and I have shown you with an example. When you have two same terms, they are gone.
Yes.
X
Yes,
cube
sir.
minus x cube 0, x power 6 minus x power 6 0. Only x power 4 is remaining. Those who are following mathematically, I'm trying to prove you the theorem.
Yes.
Now again, I have
X,
x cube is
X.
here.
X.
Yes,
X.
I have to multiply with x. X cube into x. X power
X
4
power 4.
plus
X
x into x.
Yeah.
X square plus
X.
1 into x. X. Now I'll subtract this. This is gone. X square plus x is the remainder. If you convert this into my R terms, or CRC terms, first position is 0, second position is 1, third position is 1. X square plus x plus 0. That means
Yes.
x power 0, x power 1, x power 2. 1, 1, 0. Did I get it? Right? So that's not a simple modular division, 2 division that we have performed. 1 by 1 is 0, 1, 1, 0 on 0 is 0. Discard the leftmost bit. This is plain terms of explanation. That is meaning behind it. That is for your understanding, easy understanding. But this is how a CRC division works based on polynomials. So this is the inner strength of your CRC. I wanted to explain. Lot of times, lot of people don't want to explain all this. And to understand this, it took me lot of, not today, when I was first studying CN, it took me lot of days to understand this polynomial concept and why it is implemented into it. And there was one full book written only on polynomials to use here. One full book. Right. Okay. Anyway, that's fine. So did you understand, Madam Srija? Why should we use polynomials? She asked the question. I think she didn't listen to me. Srija. See? Done. Let it be. So that's how a CRC works. Now note, the divisor in CRC or in cyclic code is normally called the generator polynomial. This one, x cube plus x plus 1. It is divisor or it is generator polynomial. The biggest question here is, this is simple. Where is it? X power 6 plus x cube is simple because that is the data, zeros and ones. The biggest question here is, how did we get this? What divisor should we exactly depend upon? Right? We cannot just take any divisor like that, because I'll tell you why. Because if I take, I'll tell in simple terms, if I take 3 as divisor, normal decimal 3 as divisor, okay, I have sent some 26 or something, I have made it 27. 27 is exactly divisible by 3, which will leave a remainder 0. Somehow 27 got corrupted, it became 30. It became 33. It became 36. They are all again exactly divisible by 3, which will leave a remainder 0. Again, the receiver will take it as the correct value. Are you understanding what I'm trying to say?
Yes, sir.
Yes, sir.
So the divisor that you are choosing should be so unique, so peculiar that this will not happen. That's the strength of this algorithm, the divisor. Okay, so don't worry. In the examination, there is never a chance that you are asked to take your own divisor. Don't blindly take a divisor. You will end up nowhere in the exam. Even if you have to write an example, please remember a specific divisor which I am using in the slides, in the textbook. Somewhere you have to remember that divisor. If not, there are some rules. It's not that simple. I've told you there is one full book on it. Okay. So anyway, in my cyclic code, the syndrome generated, if it is not equal to 0, simply you should understand that one or more bits is corrupted, which means data is corrupted. If syndrome is equal to 0, either no bit is corrupted or some bits are corrupted, but the decoder failed to detect them. Just like 27 became 30, 27 became 33. Divided by 3, again it gives you 0. So which means if the syndrome is 0, don't simply say that. In simple parity check, was it always detecting the errors? No. In two-dimensional parity check, again there was a loophole. Similarly, in CRC also, there is a chance that the receiver or the checker failed to detect the error encountered. Is that clear? So if S of x equal to 0 doesn't mean that there is no error. There are two possibilities. Either there is no error or bits are corrupted, but the decoder failed to detect them. Right? So what are not detectable? 27 is fine. 28 is detectable. 29 is detectable. 30 is not detectable. Are you understanding? 31 is detectable. 32 is detectable. 33 is not detectable if you are using 3. So what do I conclude? In cyclic code, those errors E of x that are divisible by G of x are not caught. 28 is caught, 29 is caught, 30 is not caught. Why? Because it is divisible by the same divisor. 31, 32 are caught, 33 are not. Why? Because that error is divisible by. What is the error here? Plus 3. What is the error here? Plus 6. 27 plus 6. 3 is divisible. 6 is divisible by 3. That's why they are not caught. So, generator polynomial is the most important thing here. Wisely, a generator polynomial has to be chosen and it should have some unique characteristics. So I'm not going to explain what are those characteristics, how to identify, because I told you it's not that simple. If the generator has more than one term, it's just a simple note, has more than one term, and the quotient of x power 0 is 1, which means the last bit is 1. I don't know, here. The last bit is 1. If it is 1, all single bit errors can be caught. If your generator's last bit is 1, for granted, you can take that all single bit errors can be identified. But in communication, single bit errors are more likely to happen? No, burst errors are more likely to happen, right? Done. So this is the characteristic that a good polynomial should have. Don't worry, don't go too much into it. Just try to understand, or if not, just leave it. It should have some characteristics. It should have at least 2 terms in it. Minimum 2 terms. That is the first rule. Quotient of x power 0 should be 1. This should always be 1. Without this, no generator polynomial will not be there. No way. No, it should not divide x power t plus 1 for t between 2 and n minus 1. I don't want to go into it. I told you it's a one full book that you have to read. And it should have a factor x plus 1. That you can understand. This should have a factor x plus 1. That you should understand. You know factorization? How to find factors of a given polynomial? Yeah, that is very simple, right? So it should have a factor x plus 1. Done? So don't worry. These are the divisors that are generally used in data communication. If it is CRC8, there is a polynomial divisor given to you. CRC10 uses that divisor. See, can you see a divisor which is not having 1 at the end? No, all divisors have 1 at the end, because that is the quality of a good divisor, at least one quality of that good divisor, right? So in ATM is a network which we'll understand in 4th unit, 3rd unit or 4th unit. You'll understand it there. ATM, we use that polynomial as divisor. ATM, AL is a layer of it. Again, there is another polynomial divisor. HDLC is a different type of, in 2nd unit, we'll discuss about HDLC. It uses that polynomial. In local area networks, LANs, look at the devices that they use CRC32. Look at that polynomial that that CRC code is using in the devices at data link layer level to identify the errors. At 32-bit. What is the example we are taking? 4 bits. Generally in LANs it is 32-bit division, right? So that's about CRC. See, it was simple and it is tough as well, right? So it's your wish. How you want to understand it, it's your wish. You can simply write it, the one which I have explained in a general zeros and one plain term example, you can do it. That is also giving you, that will also give you full marks. If you want to impress or if you want to perform more in an interview, network-based companies interview, you should know more, know deep, right? That's why I have explained you all this. Done. Now let's go to the last technique. Now all these techniques were only about error detection. What time is it? 1 hour is gone. Okay. So now all these techniques were only about error detection. Now again, the problem with error detection is if the receiver detects an error, the sender may have to resend the data because there is an error in the data. It should discard it. It's gone. Again, the sender has to resend it. Done. So to avoid this, if the receiver can detect as well as correct the error, change what has gone wrong, then it would be much better. The sender does not have to send it again. One such technique, error correction technique, detection and correction technique is your Hamming code, which we have again discussed in the last class. All this, the same slides I have used in the last lab, to tell you how Hamming code works. Remember, you have to generate redundant bits R0, R1, R2, dot, 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 how many ever they are. It depends on data word M. The formula is 2 power R greater than or equal to M plus R plus 1. Good. Thank you. At least there are people who are following me. Good. So we have implemented all this. All this was discussed in the last lab. I have shown you how it works. And even if an error occurs, I've shown you how which bit has corrupted will be identified. Now, one of you have asked me a question. Who was that? Can you remind me, please? In Hamming code, some of you asked me, what if more than one bit get corrupted? Who asked me, sir?
Sir, I am.
Anvesh or who?
Yes, sir, Anvesh.
Yeah, right. I told you that. I'll explain in my theoretical class. Remember?
Yes, sir.
Right now. So I'm going to now show you my last slide of this chapter. So this is all explained. Right. The last slide of my chapter. So whatever I have explained in Hamming code in my previous lab, that is helpful, useful only for detecting a single bit error. That's it. That is gone. But that technique can only help identify single bit errors only. But in communication, come on, tell me, single bit errors are less likely to happen. Burst errors will happen. Is that clear, right? So how can we use Hamming code to identify burst errors? We are not going to change the technique. The technique remains exactly the same. But what is going to happen is, look at the data. Now take the data. Let us just say the data to be transmitted is 1011011. 1, 2, 3, 4, 5, 6, 7 bits. 7 bits means I'm talking here about data plus redundant bits. This is Hamming bit, this is Hamming bit, this is Hamming bit. 4 plus 3. 4 actual data bits, 3 Hamming bits. 2 power 0 position, 2 power 1 position, 2 power 2 position. 2 power 3 position is not there. Done. So I have only 7 bits. Right? I have one more 10110110. 0110101. 1010110. So once I have this data plus Hamming bits, data plus Hamming bits, data plus Hamming bits, data plus Hamming bits. Generally, how we send? This is sent, this is sent, this is sent, this is sent. Are you understanding? One after the other is sent. But that is of no use. They can only detect single bit errors. So here what happens is, look at this slide. Instead of sending them like that, the arrow marks are pointing towards the down, which means instead of sending data like that, we send data like this. This is sent first. This is sent next. This is sent next. Instead of sending like this, we send the data like this. Right? So how my data will look like? How my data will look like? Look at this. I'm sending like this: 1 1 0 1 0 0 1 0 1 1 1 1 1 1 0 0 and so on. If a burst happens, assume that these 3 bits are corrupted. Assume that these 3 bits are corrupted. Are you understanding? Anvesh,
Yes, sir.
you following? Right, good. So assume now a burst error of 3 is happening. These 3 bits are corrupted. Now look at where those 3 bits are, because the receiver receives like this, again organizes them like this. Now look at where those 3 bits are. 1 1 0 is here. This 0 is here. It became 1. This 0 is here. It became 1. This 1 is here. It became 0. Now once the receiver organizes like this, how many bits are corrupted in this? 1 bit. How
One
many
bit.
bits are corrupted in this? 1 bit.
One
How
bit.
many bits are? Yeah. Can it now identify that single bit error? Yes.
Yes, sir.
So same Hamming code is used. Nothing gets changed. Hamming code doesn't change at all. The only change is sending the data changes. Now, I think a burst error of 3 is easy. All 3 are identified. Good. Hamming code is good. Any drawback in this technique?
Burst error of 5.
Good. Excellent, sir. Who is it, Sachin?
Yes,
Yes.
sir.
Burst error of 5, because I have 4 rows. If I have 5 bits corrupted, this bit is corrupted, this bit is also corrupted. Now, in these 3, I have Hamming code, it can correct, but in this, gone. 2 bits are corrupted. So this is good, but the length of the burst should be less than the number of rows.
Code words.
Or equal, code words, thank you, or equal, at least equal or less than the number of code words. Just like checksum, they are just broken into code words, and then each code word you'll have Hamming bits added to it. Done. So that is how Hamming code is used to check burst errors. This is not in your syllabus, but still don't know if it could be asked in the examination. I'm not going to remove it because I've taught it now, right? But understand how burst errors can be identified using Hamming code. Any doubts? Simple parity check, 2-dimensional parity check, checksum, CRC, or error detection techniques. Hamming code is a error correction technique, and even burst errors can be corrected by using Hamming code given a condition, just one condition put on it. So that's the end of your chapter, error detection and correction. One responsibility of data link layer is finished. Any doubts in this chapter before I move to the next chapter? Good. So I am stopping this. Now I am going to share the screen again. Okay. Visible?
Yes, sir.
Yes. So again, one of those interesting, important chapters. Very interesting. If you are listening to me, it will be very interesting. This is called data link control. And what happens in data link control is there are 3 things. In my previous chapter, there were 2 things: error detection, error correction. But look at this. There are 3 things in data link control: framing, especially sometimes framing is not a part of it, but still we can put it: error control, flow control. Sir, again, why error control comes here? Because there we already discussed about error, but we discussed about error correction, error detection, not controlling the error. This is different. You will see the difference. A lot of people get confused between error detection, correction, and error control. They are 2 different things. Controlling is different from detecting and correcting. Is that clear? Right. So I'll have framing, error control, flow control. Let's go ahead. Did I turn on the video recording? Yes. Yes. Okay.
Yes, sir.
Right. So this is the first thing I'm going to discuss: framing. Right. What is the use of framing? Because at data link layer level, the first responsibility, the foremost responsibility of the data link layer is framing. It has, framing, divide the data into frames, or organize, not divide, organize the data into frames, right? So it gets the data from the upper layer, which is network layer. It gets the data from the upper layer, which is network layer. That data will be organized into a frame, and the frame is sent to the lower layer. Right? That technique of organizing the data in frames is called framing, right? So this is already discussed, I think. Byte stuffing, bit stuffing is a part of framing. So this is also finished. We'll have to finish our syllabus quickly, but not done yet. It's just 25% finished. Data link layer needs to pack bits into frames so that each frame is distinguishable from the other. Then this practice of packing the bits into frames is called framing. And other envelope will distinguish the data from one another. Different data, this has different data, right? So this is a framing technique, byte oriented or a character oriented protocol. Look at the blue boxes. Data from the upper layer. Data from the byte should be framed now. So what is the concept of framing? Data from the upper layer, which is bytes, data from the upper layer, which is bytes, should be framed. So what is framing? Adding a header to it, adding a trailer to it, adding a trailer to it. Now this is a frame, not finished yet. So someone has to tell, or the receiver should understand that this is a frame that is starting here and that is ending here. So we add a special sequence to it to start and to end, called a flag sequence, if you remember. This is already discussed, flag. Now this is called as frame, and the technique of making this is called framing. How to do this framing? That is what we are going to discuss quickly. There are two types of framing: fixed framing or fixed size framing, or variable size framing. So what is a fixed size framing? The length of the frame is fixed. Once the length of the frame is fixed, what is the advantage? The receiver need not worry about where the frame starts, where the frame ends, because the size is fixed. It knows that the frame is this much only. Every frame will be this much only. So there is no problem with the receiver that the frame is starting here or ending here need not be identified. But what is the disadvantage? If you have a fixed size frame, how can you say that the data that you're receiving from the network layer will exactly fit into your frame? No chance. No chance, isn't it? So that's the disadvantage. If you have an uneven size of data coming from the upper layer, then you'll have a problem with fixed size framing. Obviously, fixed size is always problematic. So we'll go with the second one called variable size framing. Whatever the data comes from the upper layer, that much is the frame. Right? Now, the price framing is the receiver should understand where the frame started and where the frame ends. That's the problem. Done, right? So for that, we use two fields called start delimiter and end delimiter. This is my start delimiter. This is my end delimiter, which will tell me where the frame starts, where the frame ends, right? So in variable size framing, we have two techniques called byte stuffing and bit stuffing. Should I keep again explaining the same things again? Byte stuffing adds an additional byte escape sequence. Wherever there is a flag sequence or an escape sequence as a part of the data, it adds an additional escape to it. You have already implemented this in your lab. Okay, that is byte stuffing. Then bit stuffing. Instead of flag, I'll say 0610. You remember? I told you a flag is always like this, 0610. Done? Right. So that is my bit stuffing frame. So what is bit stuffing? Whenever there are 5 consecutive ones seen in the part of data, an additional 0 is stuffed into it. Why? Because we don't want the flag sequence to repeat in my data. That is called bit stuffing. That's your example there. The same example I've taken in your lab. There were 2 instances where there were consecutive 5 ones, and additional 0 is added to them. That's about framing. Finished. Done. I have 2 more topics: flow control, error control. So luckily, we can't separate those 2 topics. They go hand in hand. Flow and error control go together as a technique in our data link layer. Most important question, apart from your error detection correction techniques, flow control techniques are the most important or most repeatedly asked questions in your final examination. So put some attention. They're interesting. Anyway, you don't have to even worry about understanding them. They're very interesting. So the most important responsibilities of the data link layer are flow control and error control. Collectively, these functions are called as data link control. So if a question is asked in your examination, write about data link control techniques, you have to write flow control and error control techniques, right? Now let us quickly see what a flow control is and what an error control is. You should now understand what they are. What is the difference? Flow control refers to a set of procedures that are used to restrict the amount of data that a sender can send before waiting for an acknowledgement. Right? It's like this. To understand this flow control and error control techniques, I keep taking this example in class generally, very simple example. Let us say that I am dictating notes to you people. I am dictating notes. I am the sender, you are the receiver. You keep writing the notes. A flow control technique is something like this. I have to implement a flow control like this. I have to restrict the amount of data that I can send. How much can I talk before waiting for an acknowledgement? Which means I should make sure that whatever I have sent should be received by the receiver without any problem. I cannot just dictate 20 lines at once and imagine that you will write. Continuously dictate 20 lines without any pauses, stops in between, without waiting for an acknowledgement, without waiting for you to nod your head or raise your head and say, I'm finished with writing, say the next sentence. Is it possible? No, I can't do it. So there should be a set of procedures to understand where to stop, how to stop, and then again, when should I start the next sentence, or when should I repeat the sentence, right? Now, repeating the sentence. Error control in the data link layer is based on automatic repeat request or retransmission of data. If my flow control misses, I have dictated more lines than you could write at once. What would happen? I have to now implement a technique called error control. What is that error control? I have to identify where you have written until and repeat the remaining part of what you haven't written. Resend the frames. That is error control. Error detection? It is error control. When did error control come into place? When an error has detected. When an error has been detected. Are you understanding? Error detection helps to implement error control. Is that clear? Flow control also helps to implement error control. Error detection also helps in implementing error control. But anyway, flow control is how many frames can be sent by the sender before waiting for an acknowledgement from the receiver. Error control is when should the sender resend the same frame again. Sent frame should be transmitted again. It is called error control. Hope you understood the difference, thin gap of difference between flow control and error control. Sending the frames, controlling the speed or how many frames to be transmitted is flow control. When something goes wrong, how to resend the lost frame is error control. Now the protocols, these are the most asked questions in data link layer. In flow control and error control, these protocols are the most asked questions. Now, let us see how the data link layer can combine framing, flow control, and error control to achieve the delivery of the data from one node to the other node so that nothing is lost. That is our aim. Communication, we just keep talking that send, but how are you ensuring that the data is received? Here, these are the techniques that will ensure that the data is received. Okay. The protocols are normally implemented in software by using one of the common programming languages. It could be C, it could be Java, it could be any programming language. But what I am doing in my slides, to make our discussions language free, we have written, or I have written, the pseudocode, which means I'm not going to stick to any language. I'm not going to use the syntax of C, or I'm not going to use the syntax of Java. I'm going to write a plain pseudocode which is applicable to any language. Just plain words, kind of algorithm. Not even algorithm, pseudocode is the right word. Okay. Version of each protocol that concentrates mostly on the procedure instead of delving into the details of the language rules. I'll not go into syntax. I'll just write a procedure and you have to choose your own language. I prefer you to write in C language to implement that. What pseudocode I am writing in my slides, I want you to implement that pseudocode as a program. That will be our next week program. Right. So protocols for flow control and error control. They are broadly categorized into two types of protocols or two versions. The protocols that are used for noiseless channels, the protocols that are used for noise channels. Most of the textbooks will simply remove this. They'll simply put headings of protocols without saying noiseless, noisy. Even in your examination, you don't even have to bifurcate this, saying that protocols for noiseless channel and protocols for noisy channels. You can just omit. You can simply write protocols for flow control and error control and you can put 1 simplest, 2 stop and wait, 3 go back, and 4 selective repeat, because stop and wait will repeat in both the cases. The last one in noiseless channel and the first one is noisy channel. In the noisy channel, both are same, stop and wait. But there is a difference. When I explain, you'll get the difference why they are repeated. So let us start with the noiseless channels, flow and error control protocols. Do you want a break of 2 minutes? Anyone? Are you listening?
Yes, sir.
Yes, sir.
Good. At least few people are answering. That's really nice. Okay. Right. Do you want a break of 2 minutes? I'll just pause for 2 minutes. Stop.
Yes, sir.
Yeah, will because I've been shouting for sending frames. Flow control should be implemented.
Okay, sir.
I'll stop the recording for a minute. Pause the recording for a minute. Right. Sharing the screen now. Right. Right. So noiseless channel first. So we are trying to discuss about protocols that implement error control and flow control. So let us first assume, because we'll go with easy things first, then we will complicate the things. Let us first assume we have an ideal channel in which no frames are lost, duplicated, corrupted, damaged, whatever, nothing happens in between, which means sent, received as it is, nothing goes wrong in between. Right? So we introduce 2 protocols for this type of channel. They are called as simplest protocol, stop and wait protocol. Okay. Generally, the second algorithm is used by a lot of faculty while teaching, while giving notes. Stop and wait until an acknowledgement is seen from the student. Raise their head and then say next. We'll give the next statement to write. Okay. So that's called simple stop and wait. Anyway, simplest and stop and wait protocol. First, we'll start with simplest protocol. Right. So here, always remember, when do we have to implement stop and wait, or when do we have to implement this flow control and error control protocol? Once there is a data that is received from the network layer, it has to be framed. Remember this. Data first comes from the network layer. It has to be received by the data link layer if it is ready. Then it has to be framed. Once it is framed, then it has to be sent to the physical layer and it should be transmitted to the receiver. Now, once the receiver receives, physical layer receives. Now, again, it should be received by data link layer, right? So when there is a notification from the physical layer saying that I have received a frame, then data link layer should, if it is ready on the receiving side, it should take that frame. It should remove those headers, trailers, flags, everything. Only data has to be extracted. That data should be given to the network layer. Is that clear? This is the procedure. Sender side, data should come from network layer. It should be framed, sent. Receiver side, data should be notified by the physical layer, received by data link layer, remove the headers, trailers, data should be present to the network layer. So first I'll show you the 2 green rectangles. Can you see those 2 green rectangles there? The left one is on the sender side, right one is on the receiver side. Now on the sender side, above the green rectangle, what should happen first? Request from network layer. That is what should happen. Network layer should send the data to data link layer. It should request, I'm sending you a packet, make it a frame. That's what request from network layer should come. Now, once the request comes, what is happening? Algorithm is implemented now for the sender side. It could be simplest, it could be stop and wait, it could be any algorithm. A framing is done and then flow control technique is implemented in it. Then it is sent. Now the receiver side, look at the receiver side. What should happen? Look at the green rectangle on the receiver side from bottom. What is it? Notification from physical layer. Yes, physical layer should notify. I have received some frame. I have received some data. Take it and frame it. Now it should take it and then it should apply some algorithm there again. Sender's algorithm will be different. Receiver's algorithm will be different. Sender's program will be different. Receiver's program will be different. What should be the receiver program? Remove those headers, trailers. The data should be extracted and then sent to network layer, right? So now I'll come to the top part of the diagram, sender side. Sender side, I have 3 parts in it: network layer, data link layer, physical layer, white box, yellow box, and the white box. So get data from network layer, Data link layer will do whatever it wants to do. That's why it is in yellow now. That is what we are concentrating now. Give it to physical layer. Physical layer will send it over the transmission medium. Data frames are sent. The blue rectangles, small rectangles are the data to be sent, frames to be sent. They are being sent. Receiving side, physical layer will receive those frames. It will give it to data link layer. Data link layer will do something. That's why it is in yellow color. What is being done, we will discuss now. Then it gives the remaining data to the network layer, right? So this is how a simplest protocol works. Nothing is lost, nothing is damaged. Sender sends, receiver receives. I am blindly assuming that the receiver will receive data at any cost. No error will encounter, nothing will go wrong. That's why it is called simplest protocol. But it is not the ideal case, right? Generally, will that happen? Never ever will happen like that. Nothing will go wrong. Receiver will receive perfectly. All that is wrong. But still, we'll just understand the algorithm first, because we have to start from the simplest thing first. So this is my sender side algorithm, right? You are not required to write any program in the examination, theoretical examination, but you will need this in your lab, right? So what is the sender doing? While true, because it will always receive data from network layer. It's always true. But what should it wait for? Look at, once you come into the loop, what should it wait for? Request from network layer. What will be that request? That's an event, right? So wait until event happens. Wait for event. The sender is waiting. Data link layer program. I'm talking about only data link layer program now. Sender here is a data link layer of the sender. It is waiting for what? Waiting for an event. What is that event? Now come next. If that event is what? A request to send. Request from network layer. If the event to happen, you are waiting for it. If it happens, and what is that event to happen? Requested to send from the network layer. If event is requested to send, then perform this. What are you supposed to perform? Get the data from the network layer, get data. Then once you get the data from the network layer, add header to it, trailer to it, you know, all that. What is it? Framing. Make a frame. See that? Next step. Make frame. I'm not writing any code here. I'm just giving you pseudo code. Make frame. Then once I have the frame ready, send the frame. That's the sender algorithm. Finished. That's it. I'll change this program when I go to the next algorithms, because they have different approach. Here, the approach is nothing goes wrong. Sender plain simply sends the data, assuming that the receiver at any cost receives data, that too healthy data, uncorrupted data. Data is never lost. That's why sender's algorithm is very simple here. Now, when I go to the next algorithm, sender's algorithm will get complicated. Not complicated, extended a little bit, right? So wait for event. And if that event is requested to send, then take that data, get the data, make a frame, send the frame. Okay, that's very simple algorithm. Now the receiver side algorithm. While true, obviously, while true, always it should happen. Wait for event. Now, what is the event? Notification from the physical layer. Is that correct? Yes, physical layer notification. So wait for event. If event is arrival notification. If event is arrival notification, then data link layer should understand, there is something that is received by the physical layer. Now, what should it do? If go in, receive that frame. Receive the frame, extract the data. What is extracting data? Remove headers, trailers, all that. Only the data has to be extracted. Yes, that data should be delivered to the upper layer. Deliver data. That's it. A simple algorithm on sending side and simple algorithm on the receiving side, right? Now, this is the example that I'm going to show you. Figure 11.7, which is in my next slide. This is what you should write in the theoretical examination if asked, if a question is asked. Not the, even if you write the program, you get good marks. You will not lose at least a single mark. But this is what you are expected or supposed to write in theoretical exam. I have a sender. This is S, or you can even write it inside. I have a receiver. This is the time flow of the sending side and the receiving side. Time. That's why you see in the diagram there, my slides are tilted. I mean, my frames are tilted, because sending side will send, the receiving side will receive after a while, few nanoseconds at least a small delay, isn't it? That's why it is just slided towards the receiving side. So whenever there is a request, see, when is a frame being sent by the sender to the receiver? On the left side, can you see it? Whenever there is a request from the network layer. What is my algorithm? Get data, make frame, send frame. See that? See that here? Whenever there is a request, there is a frame being transmitted. And on the receiving side, when is it being received? Arrival notification. Can you see that? Outside, arrival. Whenever there is an arrival notification, data link layer receives the frame. That's it. Very simple algorithm. Send whenever there is a request, receive whenever there is a notification. That's it. Nothing is wrong here. Nothing goes wrong here. Understood? I did not even go into the actual techniques. Did you simply understand what a sender does and what a receiver does, especially the data link layer of the sender, flow control technique, error control technique, and the data link layer of the receiver, flow control technique and error control technique. Simplest algorithm. Any doubts? Can I
No,
go
sir.
ahead? No, good. Thank you. Right. So now, in real time, that is not the case. There will never be a chance that the channel is ideal. Can someone notify me? Notification request. It's 3 minutes more because I have a class continued from 12 to 1 again. So I have to take a rest of 10 minutes in between. I'll stop exactly at 11:50 with this price. So now my stop and wait protocol, because in real time, there is never a chance that the channel is ideal and nothing goes wrong. Who is saying that? Communication is said to be prone to be, damaged, error, can encounter, can occur, right? So if something goes wrong, how to handle it? So simplest algorithm cannot work. We'll go to a new protocol, even in noiseless channel, a simple protocol called stop and wait protocol. What is a stop and wait protocol? I'll now explain with my example. I dictate a sentence. I feel that at least this much of sentence can be happily received by the receiver. I unlock the session again and lock it again and then take the screenshots again. Don't worry. Okay, so I'll understand that this much of sentence can be sent to the receiver. They can easily receive it and write it in their notes. And then again, I cannot send the next statement until at least one of the students in the class raise their head to look at me. If one of them look at me, then I understand now, my frame is received. Then I can send the next frame. What is happening here is send a frame and wait for an acknowledgement from the receiver. Once sender receives an acknowledgement, you look at me like that. Then sender will send the next frame. Again, send the next frame and wait for an acknowledgement for that frame again. So this is why the algorithm is called stop and wait. Send a frame, stop, then wait. Wait for what? Wait for an acknowledgement. Once an acknowledgement is received, send the next frame, stop, then wait. Wait for what? The next acknowledgement. That's why the technique is called stop and wait protocol. Done? Right. Now, first we'll go with the green rectangles again, as usual. The green rectangles on the sender side. Obviously, there should be a request from the network layer. Then the algorithm is implemented at the sender side. Then the algorithm is implemented at the sender side. Sent. Don't worry about what is written at the bottom there. On the receiver side, there should be a notification from the physical layer. Algorithm is implemented. Once a frame is received, algorithm is implemented. There is something else on the sender side coming from the bottom. What is it? Now receiver should send something back. Acknowledgement. Now, once an acknowledgement comes back, it comes to physical layer, right? Now, physical layer should notify the data link layer that an acknowledgement has come again. So now the sender side algorithm has changed. It's not only sending, it is also receiving an acknowledgement. It will get a request from network layer and it will also get a notification from physical layer. Two things should happen at the sender. Hope you're understanding this. My algorithm will change now. But at the receiver side, it's very simple. Receive the frame, send an acknowledgement. That's it. Receive the frame, send an acknowledgement. Done, right? So what I want to do is I want to stop here. It's 11:45. I want to stop here with this slide because once I start my algorithm, it's not going to happen. Finish now. It takes about 10 to 15 minutes minimum. Hope you are following me, understanding. Please pay attention for the next 1 or 2 classes. Data link layer is the most important layer in your syllabus. Of course, network layer and transport layer are also equally important, but this is one of the lengthiest, with a lot of roles to it. So please try to understand error control and flow control techniques. They're very easy to understand. Don't be scared of that math written or that, program written on my slides. They are very simple pseudo code. There is not even a program. It's a simple pseudo code given to you there. Okay. Okay, I'll stop with this. Give me 1 second. Let me grab a chair.